if G is group, then rho composition sigma is equal to sigma composition rho for any two congruences, rho comma sigma on G. So basically we have to prove that rho composition sigma is equal to sigma composition rho. Proof. So for this you take element here in rho composition sigma and show that the element goes in this. So take any A comma B belonging to rho composition sigma, correct? Then there exists C belonging to G such that A comma C belongs to rho and C comma B belongs to sigma, correct? By the property of composition of two relations, binary relations. So A comma C belongs to rho. A comma C belongs to rho. It implies what? See, rho is what? Rho is a congruence. Rho is a congruence. It means rho is compatible, correct? Rho is a compatible. So we can just see BC inverse A into BC inverse C, it also belongs to rho. We can just multiply by BC inverse, because since rho is what? Left compatible. So we can just multiply by BC inverse by left. So it implies what? BC inverse A and B into C inverse C is what? B into E, that is the identity, correct? You also can write here C inverse is the inverse and C inverse is the inverse of C in group G, correct? Now situation is like this. So B into B, so E is what? E is identity of group G, correct? So it implies that BC inverse A comma B belongs to rho. It implies that B comma BC inverse A belongs to rho. Since rho is what? Symmetric, we can say like this. Yeah, we can also leave here. So we have BC inverse comma B belongs to rho, correct? This we have. Now you see, now we have also C comma B belongs to sigma. Now we just post multiply by C inverse A comma B C inverse A. It again goes in sigma. Since sigma is what? Since sigma is right compatible, being congruence, it is right compatible. So CC inverse now CC inverse is what? Identity element E into A into BC inverse A belongs to sigma. Now it implies E into A is what? A and BC inverse A belongs to sigma. Now see the situation. A comma BC inverse goes in sigma, and BC inverse comma B goes in rho. So now by definition of composition of two relations, what we can say, that is A comma BC inverse belongs to sigma, and BC inverse A comma B belongs to rho. It implies what? It implies that A comma B belongs to sigma composition rho. So we have taken element A comma B in rho composition sigma, and we have proved that A comma B goes in sigma composition rho. It implies what? It implies that rho composition sigma is a subset of sigma composition rho. Similarly, we can show that sigma composition rho is a subset of rho composition sigma. So in this way, rho composition sigma and sigma composition rho becomes equal to each other. So rho composition sigma is equal to sigma composition rho. So in this way, this result is proved. So it means that if rho and sigma are congruences, for example, if you talk about the lattice of congruences on a group, then always remember that rho and sigma commute with each other. For example, this is what? This is the lattice of all equivalences on a group, correct? And this is what? Lattice of all congruences on a group, not on semigroup. Lattice of congruences, lattice of all congruences on group, and the lattice of all equivalences on a group, and this is what? Lattice of all congruences on a group. I think it is, maybe it is not visible to all of you, so I am writing here. See what it is. This is the lattice of all equivalences on a group. This is what? Lattice of all congruences on a group. So in this case, when we calculate rho composition sigma, what will be the result? It will be rho composition sigma. Why? Because as we know that when we take I am correcting my statement. I am saying that when we take the lattice of congruences on a group, correct, and when we calculate the join of two congruences, that is rho join sigma, it will be equal to rho composition sigma. As we already seen that when rho and sigma are congruences on a group, then rho and sigma commute with each other, and when rho and sigma commute with each other, we have seen in the previous, in a corollary 1.5.12, that when the relations, when the congruences commute with each other, then the join will be what? Rho composition sigma. That I want to say. Now I am writing the statement of proposition 1.8.2. Proposition 1.8.2, let G be a group with identity element E. Let G be a group if n is a normal subgroup of G, then so see what is the problem? G is a group with identity element A, correct? Now these are the three parts we have to prove. The first part is what? That if n is a normal subgroup of G, then we have to prove this relation is a congruence on n. What is this relation? It contains those elements A comma B belongs to G cross G such that AB inverse belongs to n, correct? Where n is what? Normal subgroup of G. So we have to prove that this is congruence on G. To prove it is congruence, we have to prove that it is equivalence relation as well as it is compatible relation. Compatible, you can prove that it is compatible, or you can prove it is right compatible as well as left compatible. So this is the first part. And after that, for each G in G, then rho n class, that is G rho n, because this is a relation. So this is what? This is the rho n class, correct? Rho gn is coincides with the coset ng. That it means that we have to prove G rho n is equal to ng. For this, what we have to do, we have to take element here and we have to show that that same element belongs to Ng. So in this way, we have to prove that these two sets are equal to each other. Correct? So this is first part. Second part is what? If rho is a congruence on a G, then E rho is what? Normal subgroup of G. Means we have to prove that E rho is a normal subgroup of G. So to prove E rho is a normal subgroup of G, we have to prove the condition of normality. Correct? And also we have to prove that rho is equal to what? Rho n. Rho n is this, and rho is a congruence on a group G. Correct? And we have to prove that rho is equal to rho n. What is the last part? That if m and n are the normal subgroups of G, then rho m intersection rho n is equal to rho m intersection n. So we know that what is rho n, correct? So we can calculate rho m, rho n, and rho m intersection n. For example, rho m intersection n will be what? Rho m intersection L n is equal to a comma b belongs to G cross G, such that AB inverse belongs to m intersection n, correct? So we have to prove that rho m intersection rho n is equal to rho m intersection rho n. After that, we have to prove that rho m join rho n is equal to rho m composition rho n. Of course, we know that well, that rho m join rho n, since these are the congruences on group, so these congruences commute with each other, correct? So rho m join rho n will be is equal to rho m composition rho n, as we have already seen. So basically we have to prove rho m composition rho n is equal to rho m n. And what is rho m n? Rho m n is a comma b belongs to G cross G, such that AB inverse belongs to Mn, correct? So I left this proposition for all of you as an home assignment. So this is a home assignment I left for all of you. Try to do by yourself, and for any kind of problem, any doubts, all of you are free to discuss with me. So today I stop here. This is lecture 17, and in the next lecture we will do some more new concepts, that is modular lattice, semi-modular lattice. Thanks.